มาถึงเอื้อมยากข้อแรกนะคะตัว P population นะคะก็คือกลุ่มของ wild dog กับกลุ่มของ domestic dog ค่ะและส่วนของ exposure ก็คือ rabies ค่ะส่วน comparison ก็คือกลุ่มของ compare กันระหว่าง wild dog กับ domestic dog ค่ะส่วน outcome นะคะก็คือการทำ rabies vaccination โปรแกรมในหมาบ้านนะคะเวลานะคะก็ทำตั้งแต่ปี 2003 ถึง 2010 ค่ะ
บอกว่าเขาภาพในส่วนที่การแปลไปทุกคนที่มีการมีการศึกษา
ไฟฟ้านะคะ population นะคะก็คือกลุ่มของหมาป่านะคะใน wild dog กับในหมาบ้านนะคะส่วน exposure ก็คือ rabies ค่ะ comparison นะคะก็คือการเปรียบเทียบกันระหว่างใน wild dog กับ domestic dog ค่ะ outcome นะคะก็คือการทำ rabies vaccination โปรแกรมในหมาบ้านค่ะช่วงเวลาก็คือในระหว่าง 2003 ถึง 2010 ค่ะในกลุ่มของหมาบ้านนะคะซึ่งมี 30,000 ถึง 60,000 ตัว
So there are two pieces to this so it is mostly right. One is that wild dogs went locally extinct due to an outbreak, and that was part of the outbreak along with the lions and other things that brought people had rabies brought to mind. And then the rest is correct about the domestic dogs were the recipient of the vaccine control program. So there is both the part of the wildlife reservoir for rabies, the ecology of rabies, and then the domestic dog was the key in the end. So I would say mostly right, but just wanted to make sure that
E is for exposure to rabies virus.
Yeah. And at the beginning they did not know if it was distemper or rabies, but it was rabies.
เข้าใจไหมคะก็คือส่วนใหญ่ก็ถูกแต่ว่าตอนแรกที่เขาทำอะไรตอนแรกที่เขาต้องแยกเขาเป็นสิ่งนี้มาแล้วปัญหาที่การเข้าไปลายดิรู้สึกกินเลยรู้สึกได้ก็ต้องรับQuestion one. Please, can you have one? An, กลุ่มอันค่ะกลุ่มที่อันกลุ่มที่ข้อที่2ค่ะ
เรื่องมา2โรคนะคะโรคแรกคือทีวีค่ะก็เชื้อเป็นตัวแบคทีเรียคือเชื้อเป็นตัวแบคทีเรียคือตัวที่แบบทำโมบิลทีเรียแล้วก็ทางมิชชั่นนี้คือโดยแอโรโซลนะคะแล้วก็ฟูจิชั่นนะคะแล้วก็ในคอนแทคนะคะแล้วก็ทำดิ้ง ก็ ก็การติดต่อนะคะเราเรียกเป็นของกลุ่มคือมีแม่ไลฟ์จอบแล้วก็ไวไลฟ์ก็คือสามารถติดต่อได้ถึงการถ่ายทอดถ้ามีใครบางคนที่อยากมีเชื้อที่ดีก็จะเป็นที่ต่อไปโรคหนึ่งที่เริ่มมาคือเลสไนเกิดจากตัวเลสไนอะไรแล้วก็เกิดจากเริ่มต้นคือจากนมที่ป่วยที่มีเชื้อแล้วก็อยู่มาจากตัวนกที่มีเชื้อนะคะก็ถ้าไปกัดนกในส่วนที่ปกติดีนะคะก็จะป่วยนะคะในการถ้าไปกัดคนก็จะเป็น
I think that's good. I think one thing that we probably haven't gone over in much detail, but that everybody should be thinking of a little bit more, and maybe we'll try to prepare a slide as a bit of a review of this. But when we talk about transmission routes, which is a very important part of epidemiology of any disease, we should really specify exactly how transmission occurs. So whether it's from aerosolization, the breathing, and I breathe it to him, he breathes it in, or if it's from fecal-oral transmission, so with many parasites. I think everybody knows these different aspects, and I think that when we're talking about something like TB, it's important to explain, in detail. Well, a little bit more, not just the transmission occurs from me to him, but or from animals to people and people to animals, but also exactly how that occurs. So when you're thinking of the epidemiology of different diseases, when you talk about transmission, it's not only from which animals to which animals, and whether it's horizontal and vertical. Yes? As routes of transmission? Yes? No? Okay. So that's at one level, but at the other level is exactly through what kinds of routes. So I think you all know that. Just keep that in mind when you're talking about epidemiology of different diseases.
And also, just one thing, I reiterate exactly what Chris says. Sometimes people get a little bit vague when they're asked to describe the epidemiology of a disease. They say, it's food, transmitted by food. But what kind of food? Is it always transmitted by food? What would you say the kind of food, what food, if you like, if you're talking to humans, would bovine tuberculosis, again, you've got to define what kind of tuberculosis. Is it Mycobacterium tuberculosis or Mycobacterium bovis? But what kind of food would humans have to eat to contract Mycobacterium bovis? What kind of food? How do humans get Mycobacterium bovis from animals? Milk. Yeah. Don't make the misconception that meat is involved in the transmission, because it's not. Even in New Zealand, for example, when animals react to TB, and they have TB in their lymph nodes, they trim out the lymph nodes and the meat goes into the supermarket. So animals with TB are sold for food. So there's never been meat-borne transmission of Mycobacterium. I hesitate to say never, because someone will always prove me wrong, but 99.9% of the time it's a milk-borne disease. So if you boil your milk, you're not going to get tuberculosis.
Thank you, Captain. So,
remember, you're becoming budding epidemiologists. Epidemiologists. And Dr. Wildlife pointed out yesterday, think scientifically. Don't talk like you were just starting out. You start to talk, use the proper scientific terminology, use the proper transmission routes, etc. Those kind of things. Very good, thank you.
Hello.
ค่ะ
ก็จะอธิบายความสำคัญของสัตว์ป่าสัตว์ฟาร์มแล้วก็คนนะคะก็จะยกตัวอย่างดีๆเหมือนกันอะไรเงี้ยก็คือเหมือนการเลี้ยงสัตว์ปศุสัตว์คือพวกวัวอะไรเงี้ยใกล้ๆพื้นที่สถานีเพาะเลี้ยงสัตว์ป่าค่ะแล้วก็โรควัณโรคเนี่ยมันสามารถแพร่จากสัตว์ป่ามาสู่วัวบ้านหรือวัวบ้านมาสู่สัตว์ป่าได้แล้วก็คนก็สามารถติดโรคจากสัตว์หรืออะไรอย่างเงี้ยได้อะค่ะก็คือมีการใช้พื้นที่ร่วมกันระหว่างคนคือคนเลี้ยงสัตว์แล้วก็เจ้าของวัวแล้วก็คนในสถานที่เพาะเลี้ยงอาหารแล้วก็สัตว์ป่าก็คือพวกสัตว์ปีกเช่นกวางเนื้อทรายวัวแดงหรืออะไรเงี้ยค่ะแล้วก็สัตว์ปศุสัตว์ก็คือพวกวัวเงี้ยก็สามารถแพร่โรคแพร่เชื้อวัณโรคได้กันได้อาจจะเสพ
That's fine. My only comment, as before, is sometimes it's very easy to say, oh yeah, the disease goes from deer to animals to cattle to humans. But I think sometimes you're put on the spot now. I know you have to think very quickly. But you've got to think more scientifically than that. The best thing, if we had time, I would say to you, come and draw the relationships on a web, on a diagram. What's the exact way that, does TB go from deer to humans? Well, probably not, unless deer produce milk, which they don't for humans anyway. So, you've really got to be able to understand the transmission routes in depth. So I sort of urge you to go back and look at these diseases and actually map out the transmission routes. Very, very important to understand a lot of the descriptive epidemiology of these diseases. But you're quite right, there's webs of causation that are quite complex sometimes. Thank you.
ขอบคุณค่ะทีนี้ค่ะที่ยังไม่มีเวลาแล้ว
เรามีข้อที่4เราไม่มีเวลาแล้ว เพราะฉะนั้นอันนี้ยังไงดีคะให้เลยไหมให้เลยแล้วกันแบ่งๆทุกคนด้วยนะคะที่วันนี้ขอบคุณมากค่ะสำหรับกิจกรรมตอนเช้านะคะน้องพยายามตั้งใจดีมากเลยขอบคุณสำหรับความตั้งใจนั้นนะคะวันนี้เนี่ยจริงๆแล้วอย่างที่บอกนะคะเราจะโฟกัสในเรื่องของว่าเราจะทำส่วนทำได้ไงว่าเราจะดีไซน์โปรโตคอลสำหรับเอาเบรกได้ยังไงนะคะแล้วก็หรือแม้แต่ว่าเราจะทำWildlife Outbreak Response and Control Plan ได้ยังไงซึ่งวันนี้จะมีวิทยากรหลัก3ท่านนะคะก็จะมีคุณดาวินิกคุณคริสแล้วก็อาจารย์บริพัฒน์มาพูดถึงเรื่องนี้นะคะเดี๋ยวพี่ก็จะยกเวทีนี้ให้ท่านอาจารย์ดาวินิกนะคะ
You're on, Maestro. Yeah.
I've forgotten my good morning word already. I only knew one word and now I'm bad. Okay, conjecture. Oh yeah, she's okay. Okay. So I think this morning I will first give you an overview of basic outbreak response. Who here has ever had a class on outbreak response? FETP guys, raise your hand. Yeah, okay, so you can correct me. You are the teacher's assistant for this, and tell me if I'm wrong. So, as we talked about yesterday, there are methods or methodologies that increase the science-based approach to outbreak response, and this is the one that is accepted around the world and used by WHO, human health people, but also now in the animal health world. And we'll see if you guys have any newer information than me as a result of your training. I did want to mention what Chris or somebody, Stan, mentioned yesterday. This folder here will be part of your materials, and what we are trying to do is give you the PDFs of references that we use throughout the entire workshop. So there are numerous, as well as some documents that we found that we think would be useful for you to have. So we're helping you with the beginning of your literature search, even though you still have homework to go to those websites. So anyway, we will continue to add to this. Just wanted to reinforce that. So today we'll first start with just the basics, didactics of moving through an outbreak investigation, and then Dr. Borpat will lead us in a case problem-based learning and continue to talk about these principles. And as I go through this, I'm hoping that Dr. Borpat, Stan, and Chris will help me. I want to stop at times through this presentation and discuss some of these points. Okay? And I know there may be different difficulties in some of the translations, but we want to discuss a few of these points through here. Okay? So, hey, look at that. I wrote in Thai, huh? Can you see that? I didn't do that.
That's called click to add text.
It's magic.
That's Bill Gates.
Yeah. Wow. I had no other words on this slide. I'm sleeping in Thailand and I'm learning as I sleep. Okay. Sorry. Okay. So I have written more on these slides because you're getting copies of these and you're getting them in your handouts or your workbooks. So hopefully the slides will describe the process. Even though they have too many words for good presentation, they'll help you remember as you print them out and look at them later. Okay? So FETP guys, stick with me here. Okay? So an outbreak, the confirmed presence of disease, clinically expressed or not, right? So you may not see it. You can have disease outbreaks happening immunologically before the clinical signs in at least one individual in a defined location, in a space, during a specific period of time. Remember, epidemiology, space, and time. It is implied that there is an increase in reported cases or an unusual cluster, right? So it's an increase. And often people use the word epidemic and outbreak the same, but we'll talk more about that. So really the basic fundamental definition of an outbreak is what you are observing is more than what you expected to see. And this is where we get into very sometimes difficult discussions with wildlife, because you compare to a baseline. Does everybody know that in English? You're getting the translation as well, but the baseline. The baseline is what's expected. And when it's above that, it's an outbreak. And the process of outbreak investigation is often trying to discover if what you're seeing is more than expected. It's very difficult at times. So in wildlife especially, how do we know what to expect? That is difficult. So another thing that you guys as wildlife veterinarians and new to the system, meaning that the system is not used to having wildlife veterinarians involved, is trying to establish baselines. And we'll talk about that more this afternoon as well. Because without baselines, you can't necessarily define an outbreak. You know when something's bad and you want to do something about it, but you can't do the comparison of observed is greater than expected. So an epidemic officially, right, is basically the same definition. The occurrence of disease or other health-related events. Remember, you could talk about injuries. So there's very good literature where I live in Kampala, Uganda, on motorcycle accidents. So there are many motorcycle taxis called boda boda there, and very few people wear helmets. And so there's a lot of epidemiology and outbreaks of head injuries on these boda bodas, and there's an association with rainfall, rainy season, right? Makes sense? Very bad rains, very bad roads, and increased. So people do investigate the reasons and causes for things like injuries. Occupational safety, right? And workers at factories and things like that. So there's many applications that you could use this for if you wanted to. Chronic diseases are another thing that is interesting to talk about with that. And then just remember that, you know, epizootic is the official word for animals, right? Every time we have animals, you add zoo in there. It's English. Pandemic. Does everybody know this word? You guys know all these? Okay, good. So pandemic, huge epidemic, right? Long distances, several continents, influenza. You've heard many, many things about that. And zoonotic. Okay. So why investigate outbreaks? Somewhat obvious, yes? Well, officially there are numerous kinds of things to think about. Describing new diseases, identifying source, evaluating control strategies, right? So if you've changed, the ministry changes rules overnight, and for whatever reason, a big political thing, and you want to evaluate the results of that sometimes, that happens a lot in occupational safety, where new regulations come in at different times, and you want to evaluate the difference. You can see the rest. Again, we've talked some about this. This is important, huh? So because you have to, the example yesterday that Chris gave, this happens to us many times. Okay, so I will not continue to just give you the basics that you already know, but to build the blocks of the pieces, because this is a logical argument, right? So you should be able to talk about outbreak investigation and give this logical arguments and logical flow. So it's important that outbreak investigations are really about evaluating strategies and identifying ways to handle situations. And maybe the most important piece of all, besides the diagnosis, is evaluating these gaps in information, which help guide research strategic needs. Okay, so we'll talk more about that. Okay, so these are the steps. And there are numerous papers that we will put in your folder for in the scientific literature about the methodology. And then if you just do any Google Scholar search, you will find hundreds, if not thousands, of papers on the results of outbreak investigation. Rarely will they be written in this context, but you will usually find most of the information in there. So this is a logical flow to the process, but that is not always evident in the publications of outbreak investigation. Sometimes that's because people don't do it very well. Other times it's just not that interesting to go through in this flow every single time, although I prefer it because I like things simple. So, establishing case definitions, we'll talk about that, very important. Confirming those cases, establishing the background, the baseline level of disease, finding the cases, and then comparing those to the background, saying, is this an outbreak or not? Or is this just something going on that we should expect and deal with all the time? And then do the descriptive epidemiology, generate some real hypotheses as to the cause, and design a study, cohort, case control, things like that, to study or to test the hypotheses in order to get at the control. And then the environmental issues as well. We can't forget that. Remember the epidemiological triad, right? Somebody just mentioned it in their answer in the question. Okay, so, and then implement this, and again, remember that iterative circle that we talk about, where many times you have to go around and around in this in order to get at the answer, fine-tune your answers. Okay, so let's go through these. And these are just going to be some definitions, so the next hour of definitions, because you need to learn the language of outbreak investigation. Then we will practice applying the language. Okay? So, a case definition. There are two types of case definitions. There's a clinical and a diagnostic case definition. And it's very important because if someone has an outbreak, right, so let's keep talking about Nipah because we've been in that. What you first see are sick and dying pigs or people, right? You don't have a diagnosis. You don't have a standard diagnostic test that creates the case definition. What you have is a syndrome that you're seeing clinically. So the first thing you do is standardize that definition of what you see clinically. It can be your blood test results, your autopsy or necropsy results. It can just be a syndromic respiratory with rash, those kinds of things, right? So it's a standard set of criteria that you apply to each individual and say yes or no. So you describe it, you lay out the pieces, and you say, does this person or pig or bat fit this, yes or no, right? And if without that standard, then it's difficult to go further in an outbreak, in a scientific outbreak investigation. So you can see just different kinds of measures, right? Could be the temperature, fever, those kinds of things. It usually includes the time frame. So it looked like this in the last 10 days or the last 24 hours. Foodborne outbreaks, right? Toxicosis, the last 6 hours sometimes, staff. The place in these villages or this region or this city or this building. And then you usually include what it is not as well. Right? So they did not have a fever, or they were not vomiting, but did have diarrhea. Things like that. Right? So you want to have as many details as you can have. Now in reality, in the beginning, much of the time, you don't have a lot of details. So the iterative approach is that it first looks like a syndrome, then maybe you run some blood tests, right? And then you know what the blood parameters are. So you have a new updated clinical definition based upon that. Maybe you get some radiographs quickly, and you have a new definition. But that's all before you get to a diagnostic test, although a radiograph is a diagnostic test. So the more information you get, the more your case definition is updated sometimes. So it's difficult because you may have a definition and you start counting, and then you have a new definition. You have to start counting over. And that's what happens is you go kind of around and around trying to figure out and fine-tune and become precise about your cases versus your non-cases. Okay? So they should be applied consistently. So in West Nile virus, in the United States, we started with dead birds. Don't know why. That was the case definition. So we were counting dead birds. Then it was count dead corvids, because it was mostly crows at the time, right, and a few other species as well. And so we did that. And then they didn't have a diagnostic test, so then they invented a diagnostic test. And we said, so also PCR, virus isolation, we know what it looks like now. So now we know it's these kinds of dead birds, and we know we have a diagnostic. So we have a clinical and a diagnostic case definition. So we went to continued counting. Well, then they changed the diagnostic test again, and we had to change the case definition. So all of our previous material that we called positive, we had to start back over and redo that on the new case definition. And for the CDC in the U.S., they had a new case definition the first 5 years of West Nile outbreak. So every year we would have this national meeting and they'd say, oh, the new case definition, and we'd go back, recount our data, recalculate everything. So I have different answers for West Nile virus depending on which year you want. But it's an important lesson, right? And avian influenza, Nipah, SARS, all examples of things that your region has gone through in the same way. So with emerging diseases, right, that happens a lot because we're learning. But for something like tuberculosis, maybe not, right, except for maybe resistance patterns. Tuberculosis has old case definitions that we can still use, mostly. Okay? Does that make sense? We okay with case definition? Okay, good. So I've also covered the diagnostic one here, right? Standard tests. So when you talk about surveillance, and you talk about what tests, you have to differentiate between what tests are possible and the issue of them being validated, not validated for different species, right? Because we're wildlife people and it's harder. But also, what should be the standard, most reliable case definition? And that's what we hope to get to, that often is very difficult with both emergence and wildlife, the emergence of new diagnostic tests. Okay? So keep that in mind as you choose your diagnostic test. Maybe it's best to start with all possible tests. Then rate how valid they are, right? Sensitivity and specificity, how you choose your test. And interestingly enough, I don't know how it is in Thailand, but in the USA, to get sensitivity and specificity information on diagnostic tests is not always very easy, because the companies do the testing of their own test, and they don't like to share that data unless it's 100% and 95%. But if it's 88% and 72%, they don't like to tell you that. So then you have to look in the research and the literature and let scientists who have done the validation studies separate tell you that the test may be not quite as good as you want. So it's not always as easy as looking in the book and saying sensitivity for avian influenza, right? And so this is not easy many times. But we try and get to a point where we have consistent definition of the tests that we define positively. Okay? So hopefully someday we get to a final case definition. So I said, for example, the official case definition for West Nile virus, updated every year by both the CDC, the Human Health Authority, and the Animal Health Authority. And they weren't always the same. So the case definition for horses, for diagnostic, not always the same for people, not always the same for birds. So it was even more complex. I guess I just said that. So in the end, they did come up with some standard testing for all. So it was PCR and virus isolation standard. But then when we did serology, there was plaque reduction neutralization and numerous other assays on top of that, and we had a whole flow matrix where it could be negative based on too low of a titer, it could be flavivirus positive, it could be St. Louis encephalitis positive, it could be West Nile virus positive, or it could be kind of unknown. I mean, we had many different answers for serology. So our clinical investigations for wildlife, because remember, virus isolation, PCR, you need tissues. Often they need to be dead for those tissues that they wanted. They wanted liver, kidney, spleen. So those dead things were easy. But the live things that we cared about, especially in zoos, were often very difficult because the serology flowchart for our case definition was very complex. we're getting ready to publish this as well, and maybe I'll make sure I send the publication of 6 years of new data so you can read that. Okay, so once you have that case definition, you have case confirmation, right? So you verify the diagnosis, you make sure you have confirmatory tests, you make sure everything that you're seeing fits or does not fit your case definition. You really have to make sure that with new diagnostics, your laboratory error, right? People are inventing things very quickly. You have to go back and work with them on that. Look at the issues of false positives, false negatives. That gets into not the sensitivity and specificity, but the predictive values, right? So this is the application of these diagnostic tests, and how much do you believe the answer? These are, in emerging diseases, very low prevalence, right? And we know that low prevalence diseases will affect the predictive values based on the graph I showed you yesterday. We didn't go as much into that as we should have. But if you don't have much disease, then it's harder to believe that it's positive because you expect less. Right? It's easy to believe it's negative because 99 out of 100 will be negative. So you think, oh yeah, it's good at defining that with low prevalence. But how much do we really believe that that one is positive? Because we know there's not much of this out there. Okay? And so we can do the math behind that, and that's what those graphs are. Okay? It's good to work with your diagnostician friends on this part. And keep really, really good records. Every time things get updated, you have to keep all of the old records in the archive and then use the new definitions and update everything. But keep all of those old files. Because I once had to go back and show, this was in a retrospective analysis, this was our West Nile virus definition in the year 2000. And here was the picture. But with today's case definition, the situation looks much different because we use different tests that we believe are better now. This is also the reason to archive your samples, right? So one goal, one good initiative is to find a way to have sample archives in the parks or near the parks where you live, or make sure there's a central repository, maybe upstairs here or wherever your home base is, that's keeping samples. And those samples must be properly identified. Barcode technology, right? Those beep with the little barcodes is very good. People are using those now. So some basic initiatives for you guys before research are looking at monitoring your populations. We're going to talk more about that. Looking at how you would store samples, building some infrastructure, writing some grants together, getting permission for money from the ministries to set up the infrastructure to save samples, to record data, to look at things the same way, standardize the way that you look at things between yourselves. We're going to do more of that this afternoon. Okay? So, case confirmation, this is now the way you finally have agreed, your diagnosticians, your politicians, this is a positive, this is a negative, and many times you have these kind of, well, it's not positive or negative, it's a suspect. You have to figure out what to do with those, because if you have positive, negative, and suspect, and you need to calculate a rate of prevalence, what do you do with the suspect? So often you will calculate 2 times with the suspect as positive and the suspect as negative, or you'll take them out. And you have to be very clear on how you're doing that, because it affects the answer very much, right? So you try not to have this middle definition, but in reality, you often are forced to deal with this middle definition. Okay? So that's why you work with the diagnostician. We need to really say, let's decide here the best we can, so you don't have this middle category of components. Okay? So then this is the hardest part for wildlife. Establishing endemic levels, normal, baseline. So using the silly FIV in tigers example, what's the expected prevalence of FIV positive in tigers in Thailand? Anybody? Right, so stupid question. But the point is, that's the answer in wildlife most of the time, right? Is we don't know. So often, the outbreak is one, because we don't know any better. Now, if it's Ebola, okay, that's important enough, we'll all accept that. But if it's tuberculosis in elephants, even though we know every elephant is important and we care, can we define an outbreak in TB in elephants? I hear that you have a very good project going on right now with the mahouts and, did I say that correctly? And the elephants, and looking at maybe establishing the prevalence rates. So that's really good, right? Because if all of a sudden 2 years from now you see a lot of tuberculosis, you can say, well, is this just normal, which is still bad, or is this a new outbreak? Is this something new and something that we really need extraordinary measures to deal with? Okay? So, establishing baselines. This makes wildlife, it's very convenient. We can do very simple epidemiology and make a big difference in wildlife. The Gombe example I showed you, we had no baseline information. We had a few studies that people had done for their summer projects or their Fulbright scholarships, giving us some information, but we had no continuous baseline. So we had really good epidemiology projects that were very simple just to establish baseline over 5 years. It makes it so that you don't need the PhD in epidemiology to do epidemiology. So we need to start thinking about establishing your normals now, right? Which is why we want you to think about prioritizing your species, prioritizing the diseases, right? Because that's how you figure out what to focus on getting normal baseline. So the criteria for things may be what will kill the wildlife. What are zoonotic diseases that will become political and affect people? Maybe those are the two things that you start with, trying to figure out baseline, right? One is a conservation question for animals, the other is public health interaction type question. Then maybe you list the diseases under the species that have the most contact. Just one approach to thinking about how to start. So, for captive or free-range wildlife, you start with very simple questions. Has this ever been reported in this species, right? A lot of times we don't even know that. As you went through your sheets yesterday, you know, you're thinking, what diseases? And there's a couple of easy ones for each one, and then you start thinking, well, TB, okay, M. bovis. Do we care about that in this, or not? You know, so the first question, wow, so that's a literature search, right? Back to the web. If not, the first case is a potential outbreak, and you start to learn about that, right? Very simple sometimes for us. If it has been reported, how common is it? And the problem is, not every case report gets published, right? So, in wildlife medicine, there's a lot of arguing over the value of case reports. And I would say the value of case reports is that when we are asking this question, one case is often important. Do we know if that can happen? Has it ever happened before? Yes, it's in the literature. Very boring in the literature because it's one case study. But it helps us say, yeah, we know it can happen. Or we publish a case series, 10 cases. Ooh, even better, right? We know this can happen more. And a better case, the best case series, is all of you guys getting together and saying, I'm making this up, but whatever kind of monkey, who has those in their parks? And who has ever seen that? And now we have case series over many different parks, and we say it's not just one animal, it's not just one outbreak, it's not just one park, but it actually happens in multiple spaces over multiple times. Now we know that we may not have the baseline, but we know that it's not one, or that it's not small, that it's more, right? So this is evidence-based approach that we learned about, right? Is you gather each piece of evidence to build the knowledge on top of it. And in wildlife, we're often starting from the very bottom, which makes it interesting, I think, right? you talk about TB in people, and you start talking about, has it ever happened in people, all of a sudden we're not very smart. And so you really need complicated statistics in humans. Okay. So the goal for these baselines is to turn this information into a prevalence or rate, right? Not just have 8 cases in this park and 6 cases in this park. If the goal is to estimate the population size and say, okay, this is a point estimate. It's a cross-sectional point estimate, not over time. But we know that we estimate the population to be 60, and we saw 6 cases. So 10%, at least in one point of time. And in this park, it's 20% or whatever. Right? Because you try and make more complex, better baseline as you go forward, which helps you establish this, is there an outbreak? And as veterinarians, you may say, well, I don't care if it's an outbreak, because if I see the disease, I'm supposed to help. But sometimes you can't cure all disease, and depending on the management philosophy in the country, which I don't know, but in East Africa, it is often, hey, if this exists, it's not our job to try and make it go away, because it's part of nature, unless it's an outbreak, and it's looking like it has conservation implications, or something like that. So you get into some of the politics of this as well. And if you can call things an outbreak and demonstrate it, and you do, for conservation reasons, want to help, sometimes by defining the outbreak and working through this method, you can get the money also. For instance, I'm on the board of a group called Morris Animal Foundation in the U.S., and we have a special pot of money for emergencies in wildlife. And you can put together a proposal in an emergency outbreak to have funds to assist you to deal with that for conservation. It's Morris Animal Foundation, one word, Morris, M-O-R-R-I-S, animalfoundation.org. And you can apply. Many people apply and say, oh, things are dying, help me, give me money. Do you think that they get money? Yes or no? No. If they apply and they say, we have an outbreak, the outbreak is established because we don't know the baseline level, but here's our estimate of the baseline level, and we're seeing more than that, and this is an important species for conservation or just for welfare, or just in general important to Thailand, and we need assistance to deal with this. Those are the kinds of proposals that people will fund, because you're organized, logical, scientific approach. Okay? Do we know the difference between prevalence and incidence? Aha. Somebody tell me. Who will tell me? Anybody? Okay.
When, for example, if we search about this, it's the people who get a disease at that time over the population, but incidence that is the new case that firstly we got the population at risk and we find the new case and we count as an incident.
Okay. Very good, very good. This is important. In English, many people often mix this up. I don't know if they do in Thailand. So people use these two terms synonymously or the same, interchangeably. So what's the incidence? And they mean prevalence. What's the prevalence? And they actually mean incidence. And for epidemiological purposes, they're two very different things. Very well described. So, prevalence, the total number of cases, or outbreaks, if you're doing it that way, of a disease or infection in a specific population, that's the denominator of the thing, right? At a designated time, or during a time period. So they're all cases during that defined period or specific point. They're the old cases, the new cases, anything that's sick now, or that was sick from this time to this time. Okay? Incidents are the new, said the magic word. So new cases. So that is what we use as we look over time, as we monitor and do surveillance and follow. Right? So one is just a crude kind of measure of the overall problem. And the other is an update of new things on given intervals. And that's very effective, very important for prospective cohorts, right? Because you have a timeline and you're watching things change over time. So it's basically saying, here's the baseline situation, but here's the newest information. Okay? So when you're in conferences or working with people in English and they're interchanging these, then you have to pay attention and sometimes ask them and correct them. Are we talking about new or are we talking about all? Okay? Did everybody hear that? He likes people or he likes to think of it as prevalence is a proportion and incidence is a rate. Everybody comfortable with proportion and rate? Okay. We can talk more about that later, but we'll have some examples, I think, that also work with that. Okay, so then the magic question. You've counted, you know your people or your animals, you know the time frame, you know the case definition, you've confirmed it, you're confident, and you start counting and you compare. Is this an outbreak? Sometimes it's just a cluster. Hey, here's a group of cases. That's a case series, right? 6 of these, and they just happen to be there. But the normal rate is 10 this year, so we don't really call it an outbreak. Okay? So what? Right? It's an outbreak. Oh, good. So what's the point? Right? So is this a condition for which adequate information exists to make decisions? If yes, start with your control measures. If no, collect more information. Is the problem ongoing? Right? So there's a certain decision tree that you go through based upon that. Many people in regulatory medicine or ministries will not implement control measures or funding for control measures unless it's an outbreak. That's the trigger. You know what I mean by that? That's the threshold. Is this an outbreak? No? Okay. Well, then you don't get the extra money to react to this. Is this an outbreak? Yes. Oh, emergency funds. Go, go, go. Right? So that's some of the important implications for this as well. So now you know there's an outbreak and you need to work on this is the last thing. The other issue is sometimes you're not real sure, but you think it is. It's not quite an outbreak yet. And so it's, again, regulatory. It's saying the levels are approaching the top end of what we expect, and therefore we believe there's an outbreak. So sometimes you try and convince people that there's a risk that this is an actual outbreak. Give us those funds now, and we can help earlier, stop things earlier. And I think this will be important maybe for your jobs as your wildlife people with limited funding and money and resources to be able to create contingency plans for going out and helping something or responding to an issue to be able to leverage that way. Okay? Regardless, if it's just a series of cases, write it up. Publish case series. We saw 6 of these kinds of cases. Maybe we would have seen 10 normally, but we want to tell you about those 6. Here was the case definition. Here's what we saw. 3 of the 6 had respiratory symptoms. 2 of the 6 had diarrhea, those kinds of things. So the next time, someone can go back and see what those series of cases look like, and it helps them get ahead and it helps yourself get ahead on the next time you see something. People don't publish those enough. For you guys, that's a way to start building your basic evidence-based library, right? It's by seeing a case, describing a case, publishing the case. Okay? So, the next is the descriptive epidemiology phase. This is really the meat, the core of the investigation. Okay? And these are the steps. So you want to organize all of your data. You want to characterize the demographics of that. You want to make an epidemic curve, which we'll spend a few minutes on. You want to characterize this both in space and time. You want to establish rates and or proportions, but usually rates, and determine risk factors. Okay? So we talked yesterday about a survey versus surveillance, right? This is when you make your survey. This is when you, in order to get to risk factors, who can define risk factors? Who wants to define risk factors? Does everybody know risk factors? I know the FCC will be happy.
As a risk factor is that something that means occasion or opportunity of individual to expose to the cause of the disease, such as the habitat of operation or the sex or age or maybe the interaction with other animals or other individuals.
Okay, very good in English. Now tell everybody in your language so that you could.
ก็สำหรับรีแฟกเตอร์ก็จะเป็นวิตามินนั้นนะครับทุกอย่างหลายๆอย่างที่จะบ่งบอกว่าประชากรนั้นหรือสัตว์นั้นมีโอกาสมากน้อยแค่ไหนครับในการที่จะได้รับ exposure ที่เราสนใจเป็นสาเหตุของโรคนั้นไม่ว่าจะเป็นในแง่ของตัวของ operation หรือตัวของสัตว์เองแล้วก็สิ่งแวดล้อมรอบๆอยู่ด้วยก็คือเราจะอธิบายในแง่ของทั้งสถานที่เวลาแล้วก็ตัวของเขาเองแล้วก็ในแง่ของการกระจายของวิตามินพวกนี้ก็ถือว่าโอเค
Any questions on that for our expert? Okay, so they are things that you think are associated with the disease. Things that you are not sure, but you think may cause risk. Okay? Things you want to assess. So the kinds of questions you start building for a survey are, you need the basic identification information. You need demographic information so that you can look and do separation by sex, age, species, whatever. The clinical information, right? This is part of your case definition. Clinical signs, diagnostic test results. But then your risk factor information. What are the things that this might have been exposed to that helped cause this? This gets at transmission. This gets at the ecology of this disease. Why did it happen? What causes it? And this is important because those are the things that you want to know that you can possibly manage for prevention and control. Right? So great job, 2 for 2 on our good definition. And then you also want to know, you want to start looking for sources of information about these. Literature searches, people, experts, things like that. It's often not that easy. So you turn these into questions that are very precise, right? You turn it into a survey. And your questions have to be questions that have, each question has a single idea. What is your gender? Not always completely single, but mostly single idea. What is your age? What did you eat? Is that a good question? No, I'm seeing it. Yeah, no. Did you eat banana? Yes or no? Did you eat rice? Yes or no? Okay? Not open-ended questions. Specific questions. So, please describe the sick animal's illness. Right? That's a bad question. There's too many possible factors, and you cannot analyze those factors. Did this animal vomit in the past 24 hours? Yes or no? That's a good one, right? Yesterday we talked about 0 or 1. Yes or no? Yes is 1, 0 is no. That you can start to analyze that. Did this animal have diarrhea within 2 days of suspected illness? A better question would be, did the animal on this farm in this village have this clinical sign in the last 2 days? Right? That's the kind of detail we're looking for. Because when you have a survey with your questions, you then will create what's called a line listing. And you've asked these questions of those that are positive and negative, those that are suspect, positive and negative, right? You survey the entire community. Because you want to find the difference between those that were sick and not sick with respect to these factors. Does that make sense? If you only do the sick ones, then you only get the numerator of the statistic. What you want is to say there are 100 people in this village, or 100 cattle in this village, and you want to know the information about all of them, so you can compare these risk factors between the sick and the not sick. And so you do what's called a line listing, and it's basically a spreadsheet, right? You can do it on paper, a spreadsheet. Last night you were creating small databases. You can use database software. It's good to use that if you have it. You can create an Access database in Microsoft Access. There are many ways to do this. There's many software that have been developed to do this. And each one of these lines is an individual. And for that individual, out of your survey, you say, okay, you give them a number, an individual identification number. This is case, or this is patient, or suspect number 1, 2, 3, date, investigator. Then all of the questions go into this, because then you can start doing some statistics at the bottom of this spreadsheet. And that's your descriptive statistics. And that's how you do a case series study as well. So you take all of these, and maybe there's 50 of them, and you put in, for clinical signs, if there's diarrhea or whatever, you put a 1 in for all those and zeros in for all those, and at the bottom, you can make a prevalence. And you can do a descriptive statistic. So you don't just want to say yes, no, yes, no, yes, no. You want to give it a code that helps you analyze it with a number. Now you could just do yes, no, and at the bottom say 66 yes and 33 no. But then you still have to do the math in the end anyway. So you might as well translate it here and give some definitions of these translations. Okay? So this is the way you start turning all of this into a spreadsheet or some way of doing your descriptive statistics. And when you have all of the summary statistics here, you can take all the cases, now the numerators, not the denominator, and you can compare what you see between all of those cases in a case series study. The next thing you do is you make an epidemic curve. And that's a histogram, a visual display of the magnitude of the outbreak over time and volume. So in this village, we had this many cases over this many weeks. So week 1, we only had 0, or we had 0. 2, we had 0. Week 3, we had 1. And now you can see the shape of that curve. You can start to, epidemic curves are a way to visualize what the outbreak looks like. But in order to do this, you have to have a case definition. You have to be able to count those cases, because this is through our standard definition, we know that we have one individual that meets that definition this week. And the first individual in an outbreak is called what? FETP guy. The index case in English. If you hear people say the index case, that was the first person, animal that was found sick. Okay? So always on the y-axis, you have the number of cases using your standard definition, and on the x, you have time scale. It can be days, hours, weeks, months, you determine. The standard for reporting for human health is weeks, because they line all the weeks up in the year, and they show the annual kind of thing. Doesn't mean you have to use it that way, but it's fairly standard. Okay, so the index case, first case seen. The shape of the curve suggests how this was introduced. We'll talk about that. So, a point source epidemic. It means that there was a single point source for the exposure. It happened in one place at one time. We all had dinner last night. Some of us ate those really cool with the fuzzy fruit. That's all. Rambutan. Oh, they would never make us sick. But if 10 people ate those and got sick this morning, then last night we were exposed. The incubation period was 12 hours, 16 hours, and I got sick first, so I'm the index case. But by lunch, 7 of you were sick, and maybe we're doing this by hours. And then you would be in this one, and we would watch. But we can go back by measuring the incubation period and knowing that foodborne outbreaks are often, if it's not a toxicosis and it's a salmonella or something, between 12 and 36 hours. We would know and be able to go back and try and trace back our exposures. Okay? So this is likely, and the reason is, right, that it goes up and then it goes down. We were not continuously exposed to something, right? We were exposed once, and people got sick, but they got better. And no new people got sick. Right? So it went up and down. It's called a common source epidemic. We all ate the same thing, and those of us got sick kind of generally in the same time, and then better. Okay? Continuous common source is where, say that we had those wonderful fruits, but we had them every day for 5 days. And some of them were bad each day. So each day, new people got sick the next day. So we have the beginning of that, right, our old one, but because each day more people are being exposed, then the sick ones stay up higher, right? The number of sick stay high. We don't just get sick and then everybody gets okay. We get sick and then more people keep getting sick because there's continuous exposure to whatever is bad. Okay? Is that clear? Continuous common source. Point common source, individual, or continuous, multiple common source. Okay? Intermittent common source would be, we are together for 2 weeks, and yesterday some of us got sick and we had our first outbreak, but then no one got sick until next Monday when it happened again. Same thing, but it was intermittent. Right? So it's repetitive. And when you get into disease modeling, you get into the dynamics of immunology and who is susceptible, who's not, who is recovered, whether you're susceptible again or you have immunity for life. Right? So you get into the issue of reinfection at times. So some diseases we know you get, but you won't get again because your immune system is strong for a long time. Others, you know, like Staph aureus, food poisoning, you know that you can get many times over and over. Okay, so this would be kind of intermittently common source again. You've got periodical outbreaks. It looks the same because the incubation periods are the same, and you can trace it back to the same kind of source. Now, it could be different, and that's part of your case definition, right? So your diagnostics, right here, this is graphing things based on case definition with the same diagnostics. So you're fairly sure these are the same disease because it's the same case definition. Sometimes it's confusing, though, when you're doing things like flu-like symptoms or fever of unknown origin. Then your case definition is very broad and it gets more complex. A propagated epidemic. Repeated exposure to the same source, but potentially spread between people and animals. Right? So it's propagating itself. It's continuous. Here it was, before it was common source, right? We all got exposed to this thing just once, or continuously, or intermittently. But we all got exposed, we did not spread between ourselves, and so we all had the same effect. Here, we were exposed, but then maybe we gave it to each other as well. Influenza, right? Nipah with the pigs. So it may be repeat, or it may be spread between, but is potentially a combination of both. So again, by studying and knowing the shape of curves, you have clues as to how the epidemic happened. If it looks like this, we say, it looks like someone was exposed, and there may be some transmission between the people or the animals. And that goes back to the ecology, the natural history of disease, and we start thinking, maybe influenza. Probably not food poisoning. Right? So, that kind of thing. Whereas here, we say, it looks like they're being exposed to the same thing over and over. So what do we have that we're doing every week that is similar? And what kinds of risks of that? You know, do people get sick after no, that's not common. Well, anyway, I'm thinking of a case where you bring in tourists every Monday, right? A tourist group from all over the world. And every Tuesday, certain animal species get sick. And you start thinking, wow, maybe it's the tourists because they come in every Monday and the next day they're sick. Or on a pig farm, you pick up potential garbage from a hotel and every Monday and you feed it out to the pigs, and every Tuesday they get sick or something. I know this happened in Uganda with a friend of mine who was something actually. So, okay, so that once you see these, you start understanding the nature of this. Then you have a mixed epidemic. So we're not often lucky enough to just have one disease going on at the same time, right? We simplify everything to one disease, but many problems are mixed infections, co-infections. Right? There's more than one problem in the population at the time. So this represents that. This is one case definition. This is another case definition. And you put them on top of each other, and you start to see, oh, look at all the people that were sick, but there's two problems going on. So when it's complex and you're investigating multiple things, sometimes you can see this kind of mixed infection issue. And this happened in Uganda during the last year's yellow fever outbreak. So there was a big yellow fever outbreak in Uganda, in the northern part of Uganda last year. First time in 40 years that it had been diagnosed as an outbreak. But they called, there were many people sick, and they called it an outbreak based on 3 diagnoses, 3 confirmed diagnoses in the beginning. So people were not sure that all of the people they were calling yellow fever were actually yellow fever because they did not meet the case definition for diagnostics, just for clinical signs. Does that make sense? So there's 100 people that look sick in a certain way. We ran diagnostics on 3 of them. Therefore, we assume all 100 are the same, because they all happen around the same time. But as they started to investigate in detail these sick people, they found that there was not only yellow fever, but there was a bad batch of the local alcohol brew, and there was maybe plague going on, and these all looked like fever of unknown origin. And so they had these different things going on. Yeah, the local alcohol, it was a bad deal. A lot of people end up dying and getting poisoned by this homemade brew, which is kind of tasty. Okay, so those are examples of some of the epidemic curves and how that helps us to investigate. Is that clear? People understand? You want to ask questions? Okay. There are many other kinds of curves that help describe things. Those are the basic ones. So then what we do after we have a curve is we do more description of our data. We look at this and we map it if we can. Right? So we want another picture. So this is West Nile virus over, I believe, a 4-year span, 99 to 2002. And the red is where it happened in the beginning, in 1999. Then the next year, the green is where it spread, where they found cases. So it was in the red and the green. And then the next year, it spread to the blue. And this is our Mississippi River. Well, actually, it's right here, Mississippi River. So it was a very political deal when it spread across the Mississippi. Because then we knew it was really moving across the country. So then year 4, they started it to here, and then by year 5, it was all the way across the country. So this is a way of visualizing your data, the spread, and it just gives you more insight into the cause. So the question is, wow, how did that spread all the way across the country in 4 years like that? Any thoughts? Any ideas? We know that West Nile virus is mosquitoes, right? Did mosquitoes fly over 5 years across the entire United States? From here to Japan? Yes? No? Okay, what about the birds, the sick birds? Did the sick birds fly all the way over here and then spread the disease? Maybe, yeah. I think this is the question of the avian influenza, right? I mean, what's the role of migratory birds? So our migrations go like this. There are some minor that go like this, but mostly like this. So we think in the first years, right, just like the avian influenza issue, that maybe the way that it gets to a new area is through birds that are not too sick to fly. In other words, they can still fly. And they maybe move it, and then the mosquitoes bite them, and then while they're still sick. But we couldn't figure out why this happened. And in the end, the answer was that, you know, we have highways and we have drainage ditches next to our highways. Does that make sense? So we build our highways up, and we have these big ditches on the sides for drainage of the water. Common highways, Well, those ditches are really good habitats when they collect water for mosquitoes. And it turns out that West Nile virus can go horizontally between mosquitoes. And so it turns out that there was slow spread through these highways, major highways that run across the country. Slow spread, slowly, among mosquitoes, and it's local ecology spread, and then some long migratory bird introduction as well, right? So it's a combination of this and a really interesting ecological study of man-made structures and effects on the landscape helping the vector of the disease move, and then the natural migration moving as well. So that was interesting. This helped us figure out, wow, how does this happen? When we think it's just mosquitoes biting birds and then people getting sick but not spreading the disease, or horses getting sick and not spreading the disease, how does this happen? Okay, so mapping your data can help you create hypotheses. So the hypothesis was Are drainage ditches next to highways helping spread the mosquito population with disease westward? That's a hypothesis that is generated out of the descriptive data. And then they designed a scientific study, a prospective cohort study, where they monitored mosquito water sites and mosquito breeding sites into the future along these highways and saw them turn positive over time. So the hypothesis was developed out of the descriptive data. And then a prospective cohort study on mosquito surveillance was designed to watch this happen over time. You see how the pieces start to fit together, right? Okay. Chris, this is your slide. So by taking our data, we also want descriptive measures, mathematical measures of the data, not just mapping, right? And so many people get confused between proportions and rates, ratios. But the basic fundamental way to remember this is the way Chris told us, which is proportion, prevalence, incidence rate. It's a good way to keep it straight in your head. But you need to know, just like incidence and prevalence are misused, proportion and rate and ratio are misused. And they tell you different things, right? So really we need to look at the equations often to make sure that we understand what it's doing. So there are many, many basic epidemiology texts that'll go through all the basic measures. I'll go over a few of them in a little bit. But it's good to probably learn those. Everybody knows the difference between morbidity and mortality, right? That's something you have to teach people often. Mortality, dead, morbidity, sick. Two very different categories of measurement, right? Be specific. Who knows fecundity? Anybody know fecundity? Anybody want to give me the definition? Very important wildlife. Do you want a microphone? She's kind of pretending like she might answer. Please. No? Okay. So, FECUN, as in Nile River, N. Fecund, DITY. Fecundity. Okay. Fecundity is a measure of offspring and successful offspring. So this is talking about how successful you are, if you're an animal or people, at making babies and having those babies survive. Okay? So it goes into the rates of infant mortality, things like that. So fecundity is another measure, especially in wildlife, when we talk about conservation and looking forward. Are these things are they increasing mortality? That's bad. Are they increasing morbidity, sickness? That's bad. Are they decreasing fecundity, or survivorship of offspring? Right? When it's endangered species, you want them to make babies. With me? Okay. We did that. Here are some other rates that are important. Attack rate. FETT guys. What is attack rate? There's 4 of you and only 2 have answered.
Attack rate is something similar to the incidence the numbers on the rate of individuals of the population actually just have the disease or disease of our concern.
So the formula is the number sick over the number potentially exposed. So in terms of our fruit, wonderful fruit, example, yesterday, it's not everyone in the room last night at dinner. It's everyone who ate the fruit. So the number sick out of those that ate the fruit. If it's influenza and we were in the bus together, it's everyone in the bus. Right? So depending on the disease, the route of transmission, it changes how you define exposure. So for eating fruit, you're only exposed if you ate it. For influenza, you're exposed if you were in the same airspace. So there's no right or wrong answer. You have to define it specifically for yourself, the situation. If you wanted to define at dinner last night as exposed to the fruit, you would have to convince me that you want your denominator to be all those at risk that were present at the dinner, and we can talk about it from there. But specifically, you would say those who had the chance to get sick and those who did. Right? Okay, so then the next is case fatality. And that's the number of deaths over the number of disease. So it's the next thing, right? So the first, you have an attack rate. Those who were exposed and those who got sick. But now, how many of those that got sick died? Two very different measures, two very important measures. Then people talk about what was the survival rate, and that's just 100% minus the percentage of the case fatality, right? The case fatality is the part that died. This is the part that lived. If you work with CDC guys or anything like that, they will be using these terms. You need to know them. Okay, so then you talk about your risk factors, right? What are the causes? So now we have space, we have a case definition, we have a picture of what the outbreak looked like, we have a map of it, we have some numerical proportions, rates, we've described what we're seeing. Now we talk about why. What are the possible risk factors? So it could be, there's poor ventilation, yes or no. There's introduction of new animals. There's bad food. There's exposure to mosquitoes, yes or no. Are you immunocompromised, yes or no. Right? Those kind of risk factors for disease. So here's the official definition. Contribute to the cause of disease. Usually it's not just one, although for food it might be, right? So we get back into how do we associate these risk factors with the presence or absence of disease. And that's when we get back into our relative risk and our odds ratios and our study design. So a bit about causation, right? Causation versus correlation. Who can tell me the difference? Anybody want to try that one? So to correlate is to be associated. Right? For something to be the cause, you have to prove that one thing caused another. Correlation just means, oh, out of all of these, we have no idea, but it seems that dinner last night was important to these sick people today. Causation says we know that eating dinner together was the cause of the people who got sick today. And again, time matters for causation, right? One thing happens, and the next has, and then there's a result. So these are called Evans postulates of causation. And these are the criteria for causal relationship. And I'm not going to go through all of these, but these are kind of an accepted international standard for how you associate causation. So prevalence higher in those exposed than those unexposed. That makes sense, right? Disease should follow exposure. So if you got exposed after you got sick, probably did not cause it, right? Fairly logical. Response to exposure should be regular or consistent. So this is that if you are poisoned over and over, it should look fairly the same each time, or it should make you sick each time. This has to do with the dose response, right? So the levels of toxicity and things. How much were you exposed to of a chemical, and does that cause disease most of the time, some of the time? Anyway. You can see the rest of these. I don't want to go all through them. They're fairly obvious, but this is the way, when people say, this caused this, then often they don't know that, and they're just saying that, and they're making assumptions based on correlation. And you need to look at these factors and really ask, do we really know the cause? Especially when it's an outbreak and you're going to do control, prevention, management strategies that cost money. Okay? So out of these, we generate hypotheses, right? So West Nile virus, we had a hypothesis that there was wild birds going up and down, north and south, introducing the disease to new places. Same thing with avian influenza. But then there was this mosquito ecology spreading across the country through small local ecology. Those are hypotheses that you then want to test. So then you start into what is the design for that. Do you just move backwards and look back at a case control, or can you do prospective, looking forward? You know, what is the appropriate type of study based upon the question? And this is the analytical phase, right? We've been in the descriptive phase. Now we're in the analytical phase. So we've talked about this, so I'm going to move quickly here. But cohort prospective studies, right, are used. You use relative risk, and you use attack rates to do that. So what was the attack rate again? People remember? Those that got sick from those exposed, right? And you can do those for the exposed population, and you can do those for the sick population and the non-sick population. So let's look at an example. So this is a zoo example, because I used to teach this in the zoo. A suspected foodborne outbreak of salmonella in a zoo's population of 12 lions is being investigated. Food items are rotated, so not all animals had the same food ingredients in the past week. So we want to conduct a risk factor exposure survey, calculate attack rates, calculate relative risk, and then find out if it's statistically significant, which is the last piece. Okay? So, we designed a short survey, right? This is my survey. Very small. And we ask those questions of each animal. Luckily in a zoo, animals have keepers. And so you can ask keepers about the exposure of animals and what they know about their animals. My questions are very, very specific. Was this animal sick, as defined by what salmonella looks like? That's my hypothesis. And so it's diarrhea, fever. Did this animal consume specific foods? And one of them is a carnivore chow. And what that is it's an industrial developed food source, nutritionally like pet foods, only for lions. And then you can ask that about all the food items. Right? So this is the typical foodborne outbreak investigation. We then make a line listing, and this is the relevant information. The different food items that we were looking at, the number that were ill, the number that were well, that ate those, and you go through that for those that ate it and those that didn't eat it. And you see that this starts to be the information for that 2x2 table, right? Where you have the disease, yes or no, the exposure, yes or no, and then you can start looking at it that way. So I've broken this down just for speed into those 4 squares of information for this food item. Does that make sense? Because that helps you then do the next thing, which is create the 2 attack rate for those exposed and those not exposed. Does that make sense based on those 2 formulas? You have an attack rate for sick, attack rate for exposed, and attack rate for not exposed. So you have answers for each of those. And you do one more piece of math. You divide the attack rate for those exposed by the attack rate for those not exposed. And you come up with what's called relative risk. People follow that? You'll have all of these slides, so you can go through and study this example for that. So don't feel that you have to write everything. Okay? So now what do we do with these relative risks? Does anybody know? Does anybody have an idea? We're trying to figure out which are the things that are most likely the source of this outbreak. Right? Which food made them sick? And we have 4 main ones that we're concerned with. We give them bones to chew on. We give them this mixed industrial diet. We gave them some hamburger, right? Just beef. And we gave them some eggs for protein sources. So any idea how to interpret this? Who wants to interpret it? Just take a guess. Which one of these do you think is most likely to have caused disease? Eggs? Why? Highest number? Okay. Okay. Good. That's the point. So the interpretation, when you're talking about relative risk, you're talking about the relative difference between exposed, not exposed, sick, and healthy. Right? So, the way that you do that is, I blew the answer. So, the number 1, if it turns out to be 1, what do you think that means? If the ratio between exposed and not exposed is 1, no difference, no suspect here, right? Because there's no difference between them. Therefore, this thing was not associated more with disease or with health. Nothing. So if it's less than 1, then not only does it not probably matter, but it's possible you could create a hypothesis where it's actually protected, right? Because it causes less disease if you ate that thing. Now, this is where biological sense or logicalness comes in, right? So it's unlikely that eating a femur bone stops you from having salmonella. But if we put in here who was exposed to antibiotics every day, and it turned out to be 0.2, then that would make sense to us, right? You get antibiotics every day, it's less than 1, so it looks protective, and antibiotics might be protective. So there are things that can make sense in this, and there are things that don't make sense. So you don't worry about it if it makes no sense. There's no hypothesis for why that would be protective. Don't worry about it, because you're really interested in what would be bad. Okay? So this, of course, anything greater than 1 is more associated, this factor is more associated with disease or badness. And the higher the number, the more association there was. So if you had 3 things above 1, one had a 1.5, the next one had a 3, and the next one had an 8. Would there be a difference? You think so. You think the 8 would be the most associated. It doesn't prove it. It just gives you a relative weight. So you would still want to investigate everything higher than 1 because it has a positive association. So don't just pick the highest one and investigate that further. Look at them and say, most things are caused by more than one factor. So let's investigate those factors all. Okay? So this just describes that whole picture and talks about that 1 is the central thing. Not 0, but 1. Because it's a correlation, 1 to 1. Okay? Everybody clear? Questions on that? Okay. So then you have this relative risk, which is just a number, just a correlative number, but you want to do a test. You want to do a statistical test on that and find out if it's significant. And we're not going to get into that, but there are numerous tests that will test this and give you a p-value, right? People know the p-value. 0.05. Everybody's familiar. Not as we start into statistics for the next one, and a whole other story. But there are certain programs where you can do it the long way with a statistics book, but there are certain programs where you can test this at the CDC website. So the Centers for Disease Control and Prevention, cdc.gov, is a program called EpiInfo. And it is their, the FETP guys probably know this, it's their software, like you learned last night. It's a different set of software that CDC does its training on. And they have an interesting calculator for these different rates and things like that. It's free. You can download it on the internet. It has an online manual and tutorial, and you can work through some examples as well if you want to follow up on your own. It's pretty good, self-explanatory. But you want to know if it's statistically significant, because just the number 3 does not make it statistically significant. Okay? You have to turn that into a statistic. That's for another day. So remember that if we live in this world, the epidemiologic triad, we have been focusing very much on this, right? But we need this part in our investigation. We need to make sure that we look at environmental factors. In the food investigation, we may care, we may not. But somehow, those wonderful fruits got contaminated. And they were contaminated somewhere in the environment. Right? So the environmental investigation goes back and says, it was the food, or it was the bats. But how did the bats get it? And Deepa, how did the food get it? And it's the environmental investigation. So then it's a whole other level and a much longer kind of discussion. But it's the same process. You then go see what things in the environment you're exposed to or not exposed to, and you can do the relative risk, and you can look at environmental factors. Did you drink water from this source? Were you exposed to this pesticide? Were you traveling in a bus downtown with many people? Oh boy, sorry. I got excited. He gets excited back there too, Mr. Translator. Sorry. So this is when you do the environmental investigation. You may need to go collect samples, do contamination, heavy metals, toxicology, coliform counts in the water. So as wildlife veterinarians, you are also ecologists, right? So many of these diseases have implications for the environment. And it's very good, just like you want to work with your diagnosticians, to talk about case definition, and your pathologists, who usually know way more than us about the disease stuff, then you want to work with ecologists and maybe environmental people, environmental health people,
occupational hygiene and health people to get into the environment and the risk factors in the environment. Once you think you know this, right, so the fruits, the wonderful fruits, and they were contaminated, how did those grow? Did they grow on trees? The rum or how do they grow? Trees, vines, in the ground? Trees. Okay, so that's not a good example. If we had something that grew in the ground, and it had fertilizer, and the fertilizer had feces, so the environmental investigation would be what kind of fertilizer? Let's go sample the soil. What about the workers? And how clean are the workers who are transporting? Let's go test their hands. Right? The investigation. If this is bats, and how did bats get the disease? Well, did they evolve with it? Or are the bats getting it from somewhere? So Ebola, the first known case of Ebola in apes was a dead animal found on the edge of a village. Someone said, ooh, free food, and ate it, and got sick. Is it the gorilla's fault? Ebola? No, the gorilla died. So the gorilla was the first victim, then the person ate the gorilla was the second victim. So where did the gorilla get it? Well, let's work with ecologists on gorilla behavior, or behaviorists, ecologists, on, as Chris was saying, on studying the natural history of gorillas and trying to figure out where they got it. Right? That's the wildlife question. What is the ecology? How far back? And can we do anything about that? Or do we just have to figure out how to prevent it midway down the stream? So what we're doing now is, hey guys, if you find a dead gorilla, maybe don't eat it. Because we can't tell you where it came from, although now we know some bats and small antelope and things. But we can't prevent that. So if you eat this dead gorilla, your risk is high. We realize it is free protein, and that's very difficult. Then they say, no, we have to eat the gorilla. Wow, okay, so let's cook the gorilla. Let's wear gloves, a spacesuit, to cook the gorilla. So there's those kinds of questions that wildlife people have to address, right? They're real questions. They sound silly, but those are real things that they have to go through. You can't just go tell someone, don't eat free protein when you're starving. Because you can die quick or you can die slow, right? Okay, so, these are some of the real issues. Okay, so then there's risk communication, final thing. And we've talked a lot about this, but I would like to propose that this group at some point go through risk communication and management training. And as a result of this workshop, I would like to propose that you have a whole course on risk analysis, and that media communication training and risk communication training is part of that. You are professionals, and you are in a very difficult situation where there's emerging diseases and people will try to blame wildlife, and you need to be prepared. Have people gone through risk communication training? Maybe through the ministry or the DNP? Okay. So I will propose that this be a training for you guys, unless everybody tells me this is a bad idea and we don't want to do it. Or you can tell good Dr. Bortheim, he can tell me if you don't mind. You're too nice. But I think it's something to consider. Okay? Publish your reports. Publish your data. Even if it's simple, if it won't be accepted in a peer-reviewed scientific journal, find a way to publish a report and get your data out there. We'll talk more about that this time. Okay? So, this is the process. Establish a case definition. First, clinical, observational. Second, diagnostic. Use that case definition to confirm or deny reported possible cases. Count them. Do some descriptive statistics and compare them to the baseline and tell whether it's an outbreak. If you don't have a baseline, that's a different study. And that's a wildlife issue. Do all the descriptive epidemiology. Do the, what's it called? The different graphs we made. Epidemic curve, very good. Do the spatial mapping. Do the critical proportions and rates. Think about your risk factors. What caused this? Those are hypotheses. Find a way to test them. Do a prospective study. Do a case control study. And then think about where it came from. Go back to the environment and ask why. Why did this happen? How did this happen? You're ecologists. You're wildlife natural historians in medicine. Keep asking and pushing back. Okay? Good. Are there questions? I asked you that many times. Okay. So, FETP guys. I know you won't tell me it was bad because you won't do that in your culture. But does that cover in a somewhat similar way as the PhD guys? Or the FETP guys? Okay. Okay. So are there any big things that I left out that are important from that perspective that we need to work on? There are? Okay. Cool. What are they? Yeah. So this is the simplified version. It's not supposed to be an entire month of FETP. But, okay. So we can talk later about whether there are big pieces that we should add to this. I keep getting the microphone. Maybe I should go back here. Okay. Thanks.
โอเคค่ะย่อจากถ้าเผื่อเรียนเรื่องนี้เนี่ยอาจจะเรียนไปหลายเดือนเขาย่อมาให้เราแค่ไม่กี่ชั่วโมงนะคะเดี๋ยวเราจะพาเบรก15 นาทีนะคะกลับมาเราจะมาคุยกันต่อเรื่อง Response and Control Management แต่ว่าเมื่อกี้นี้พี่บอกแต่ว่าถ้าเผื่อเรามาเลทตอนเรามาเลทเนี่ยเราจะต้องเต้นแล้วเขาติดหนี้เขาติดหนี้เราเสร็จแล้วเขาก็เลยลงมาพร้อมกันเลยเพื่อจะมาเต้นให้เราดูอะค่ะ อยากจะนำเสนอใครให้เป็นคนนำเต้นคะเมย์ค่ะเมย์แล้วค่ะเมย์เพื่อนมา
Sacrificing you. ตัวป่วยทำไมตัวอะไรไหมตัวผมลืมไหวที่ตัวไหวไม่แบบต้องไปดูตั้งต้องไปเลย
พวกเราช่วยกันร้องนะคะไปดูไปเกี่ยวไปดูไปเกี่ยวเกี่ยวตูดซ้ายเกี่ยวตูดขวาลอยชิคกี้พายชิคกี้พายย่างถูกเผาย่างถูกเผาไปดูไปเกี่ยวไปดูไปเกี่ยวเกี่ยวตูดซ้ายเกี่ยวตูดขวาลอยชิคกี้พายชิคกี้พายค่ะพักเบรกนะคะขอ10 นาทีน้องๆแล้วกลับมาตอน 11 โมงค่ะเจอกันถาม 11 โมง
So what
bird. One to one here. They're going to the stick, going to the left, to the right. Yeah, put to the left and put to the right. Drop. Very hot, very hot.
Just a traditional children's thing, or
Yeah, it's a traditional for the workshop, like you can dance or you can dance.
Oh,
If you also have American workshop, you can do to a before. They also have, you can do it.
That's how we do it.
Oh, you can show them next time.
Yeah, I'm trying to remember how I do it. Yeah, the chicken dance. It's
That was great, yeah. I found that article, by the way, I'll stick it on there.
Found what?
I found that article.
Oh, great. Thanks. Yeah, Morse,
Stick it on there.
yeah, the Kane and Morse one?
Yeah.
No, that's, it's
Use the principles for it.
absolutely, yeah. So, and that's, I just wanted to do, really basic, run through the concept of why.
Honestly, correct.